engineering course here. So you can build a Iron Man helmet, you can build an Iron Man gun leg, you can build a Rubik's Cube solver, you can build a model kind of airplane engine, and you can build a lots of different things. I will show you around afterwards. And then we can also show that what can we do here. We can start from, because we cover a lot of different things from basic 3D modeling, manufacturing, and from the second year, we're covering some embedded systems. You learn how to making a printed circuit board. You learn how to programming, how to control a motor, how to control a sensor, how to read a sensor environmental, because that's very important for environmental monitoring. Because my primary focus, research focus, I'm a researcher as well. So my primary research focus for smart irrigation for agriculture. So I do lots of projects. Well, I'm still doing lots of projects for primary sugarcane irrigation. So we have done. So that's a let's post over there if you want to have a look. So my primary focus is auto irrigation, how to monitor the soil condition, monitor the plant condition, using the weather information, using the satellite images, how to use crop modeling to predict how much crop grows. And based on that information, we can tell farmers, today you need to irrigate 10 millimeter, tomorrow you have to irrigate 20 millimeter. And then kind of helping farmers building decision support tools. So we cover lots of that. But as I said, so we can do a lot of different things from software, hardware, printed circuit board, and image processing AI. So basically, whatever you want to make as a product, we can turn into the prototype. We can't make a commercial product at this moment, but we can definitely make some prototyping. You will see some of the project I'm working on right now. That's a fly simulator, a fruit fly sorting machine. So that's another project I'm working on right now. So that's the introduction of this space. But so what should I do now? Just showing them around the space, or Sam might have something extra to talk about.
We could do is we could start off by going through more of the automation, so the assembly line discussion, because there's been a lot of interest in relation to automation, and especially from the ag tech space. So if we demo the assembly
Space,
and then we'll move around, it would be great. Also had lots of questions around CNC, so laser cutting, especially for different modulars and for different prototypes. So if anyone's working on various different modular or CNC machine. Another question I've had is around, how we start in the electrical labs with a breadboard, with resistors, capacitors, and building on the breadboard. It moves from that lab into the space. Then you get your Arduino or Raspberry Pi. We want to show you that life cycle.
Yep.
And then down into what we call a PCB machine. So the printed circuit boards. A lot of you have asked, how do we get a prototype into like a product, right?
Yep.
So even though there is a focus on IoT prototyping, there's also been discussions around more prototyping from a lab perspective and different mechanisms between cellular prototyping. So I'm parked that for Andres. So if anyone wants to have a discussion on that particularly, but we also wanted to reach out to you to see, do you have any specific projects that you're working on right now that you would like to, see what's available, whether it be 3D printing, robotics, automation, bringing out the CNC machine, or would you rather just have a walk around to each project and it might inspire thinking? Yeah? Walk around? Excellent. All right. We're going to start on automation. Is going to be our first topic. And is anyone working on automation in any of their projects? There's a few. Okay. So we'll have a look now at a assembly line automation that we've been working on with some IoT engineering students.
Teaching focus. So.
It's more of a teaching focus, but it's I think it's really cool.
Yeah.
Right. All right. So we'll head over to the then. Okay. Right. We'll start over automation.
So this is what Sam talked about, the small production line you might see quite often in a car manufacturing or Amazon warehouse. They have some similar machine like this, but this is a miniature machine similar to that one. What we want to do here is to equip student, teach student how to. So back down there, it's the called programmable logic controller (PLC). That's very common in industrial environment. So what we teach students how to program this machine. You can see there are lots of sensors, actuator, pneumatic parts. So the function of this one is have three different stations. The first station is we call distribution station. So you have a working pieces coming down. So there's a pneumatic actuator to push the parts out here. And then there are a few different sensors to trigger that. So they will move the conveyor belt and go to the next station. Unfortunately, some glitches for this thing that some student broke last time. So we can't really demo right now. I'm sorry. But then the piece will go into this machine. So there you can see there's over sensors. If I flick this, put my fingers here, you can see there's a blinking light. That's meaning that the sensor is detecting a piece over here. Then once it detect that, the arm will go down, will grip that, and then move over here. So what this does is have a kind of measuring distance. So if the piece is in the right position, it will have a probably 30 millimeter. But if you're going upside down, it will go deeper. That means you can actually detect whether the piece is on the upside down or the wrong direction. If it is, it will be trigger that, will be rejected to this slide. If it's normal one, it will go to this one. So there are a few different sensors here, like a metallic sensor and a black sensor, basically trigger. So you only have three different colors for this, but in a real environment, you have a bunch of different sensors to trigger. Like for the Amazon warehouse, we have the box in different shape. They will automatically correct them in the right position, right? So that's similar to that. It will sort into different slide based on the color. So what we're trying to have a student is that so this machine, even though it's a miniature, but all the protocols, all the connections, they are identical to what they will see in the future if they go to a manufacturer, for example, sugar mill. That's common here in Cairns. So we also take them to the local sugar mill in Mulgrave Sugar Mill. So when they are doing the assignment, they can actually talk to the automation engineer over there to link what they study to the actual like a workforce. So after they graduate, they can directly convert their skills learned to the workforce. They don't need a lot of training. So that's what we want to cover that. And on top of that, we also want to teach them some of the industrial settings. So not just programming. Programming it's kind of easy for us. It's just software programming, but there are lots of other things you need to consider in a real industry. You can't just get as fast as you can, right? You want to make sure the production line running reliably, no one get hurt, have some safety feature. That's also something we want them to consider in its programming, and also team working as well, because these are three different stations, right? So each student will work each one of them. How do you collaborate? How do you tell this machine this is ready or this machine is ready? And when there's something happen on this machine, how do you tell each machine to stop immediately? So there's some communication so that a few different things to cover in this assignment. So they really enjoy that because they actually kind of connect them to the real industry, have them working together. It's kind of different assignment than you're just doing programming, writing reports. It's the actual thing they would do here. Okay, so that's something for the automation part of thing. This is more for the industrial automation. It's kind of different to the robotic automation, but this just follow a standard protocol. That's what you do normally when you go to an industrial automation. You don't have to follow this step to perform things, right? Yeah. Any questions for that?
I have a question.
Sure.
You mentioned that it's broken because of a student. So my question relates to, say, for example, you're a sugar mill and
Yep.
you bring this in.
Yep.
If your machinery breaks, your production shuts down.
Yes.
So do you need, commercially, would you generally need someone on site full time, or would you have somebody that you called up to bring out, or would you need a full-time person to look after the?
So the automation engineer will look up all the setup processing. So there will be also a lot of safety features on that. If it breaks up, there will be sensor that trigger. So you may have a backup system that so you don't want the system to break up. So you need to have a lot of detection. For example, one of the students working on the bearing monitoring project, so it consistently monitoring the temperature of bearing and the vibration bearing. Before it fails, you need to tell the system that there's something's failing. So in the real industry, we'll have lots of monitoring thing, either monitoring pressure, monitoring vibration to alert the operator before it just shuts down. That's about the feature. We don't want, well, here it's perfect, everything work perfectly, but in the real thing, there's so many things that could go wrong, right? Even the internet can power off, right? We don't want that. So there are lots of backup, like a duplicate system for like redundancy for the actual system. That's also what they see in the when they move here. Oh, it's so simple. I just program it. I can do it in one day. But when they actually go to sugar mill, they say, oh, we have so many redundancies. We have 1, 2, 3, 4, 5, 6, 7, 8, and we need to use like large powers for this one, and we need to have so many different switches to tell and we also need a person to see in front of computers to see the operation, because there's a screen right here. There's no screen. They only see the in operation. But we are also working with digital twin as well. Like so because we have a student from remotely as well, they can't access the machine. So we build a digital twin so they actually can operate in the software and then see this in action in real time. So there's also some part of that we're doing that. So that's generally what we do for teaching students. So this is a third-year subject. So by that time, they already quite kind of experience in programming in this hardware. And then so that's the automation part of things. I think there's some issue.
Okay. There's always an issue. But it's quite interesting seeing on and detection of defects across the assembly line. So it will
Is that
sort.
based on the size, Sam? Is it the size
Yeah.
of the defect here?
Yeah, so see it's coming along now. And so is it black? Is it red?
So there's some
Is it the right shape? Does it meet the criteria? All of those factors
there's something to be tuned.
needs to be checked.
Yeah, I have because it's just finished teaching. We haven't been able to connect that.
But it's good to see.
Yes.
Yeah.
But
See that. Extra. That's going to recognize. You can
so
see.
this is upside down, so it pick up.
Is it the height then? So that was doing the height.
Yeah, so it will reject. But if you have
Reject.
like a normal piece going, hopefully it works.
Oh, no. Yeah.
I just missed one. So there's
Try again.
uh-oh.
Ah, no.
Oh,
No detection.
this is a normal one. Hopefully pass through, so it flip that over, means that it's successful. But the third station somehow doesn't want to move at all. So there's mechanical maintenance we have to do. But anyway, I tell you a story. Yeah, so actually we want students actually to maintain this as well, but well, there are so many works to do, and it's already too much for them for doing that in 2 or 3 weeks to finish that. But that's the part of our teaching. Can we move forward?
We have to chat about the mud crab.
Let's do it. The other interesting
Yeah.
project I want to like link this one. We talk about sugar mill.
Oh,
So recently, I'm working with the sugar mill for a quite interesting project. I think it's over there. So for the car buffer decoupling, there's a sugarcane train, sugarcane car. They all two link together. When they go to the mill, they have to decouple them. So then all the car can flip over the sugarcane. So what we're doing right now, what they are doing is has a operator to pick up the pin, to lift the pin, and then flip away so the car can decouple. So what they want to do right now is building a robot that's automatically to recognize the pin, pull it out, and then move somewhere. And then on the other side, when you come back after flipping the pin, you have to put the pin back. So we have an undergrad student working on that right now. That's kind of how we link to the industry. We have some robotic link to industry. So that's also something. So what about mine as well? So the other project that I mentioned about vibration monitoring about bearing, because you have in the mining you have a lot of roller. In the roller there are lots of bearings. So those things are very will fail at some stage. So what this PhD doing is to building some small chip devices that can be like a magnetically attached to the bearing housing, and then monitor the vibration on the bearing all the time, and use some machine learning AI to detect whether there's failing, whether there's a missing ball or something like that in a different, and then send that data back to the cloud somewhere through the mesh network, and then you can see the failure immediately before it happened. Like I said, that's part of the full diagnosis kind of process that you use for signal processing. of that. So we have lots of different projects like linked to the industry. So I also built a small vacuum cleaner back
Yeah.
2 years ago. So for local manufacturer, so there was local cleaning service company. So she's not happy about the current commercial vacuum cleaner or the domestic vacuum cleaner. Oh, Dyson is it just run 30 minutes, so it's not enough for because normally they need to clean up the whole building like a 5 floor. You have 30 minutes. That means you take 10 different batteries for that. And then a normal commercial vacuum cleaner, you need to have a power cord with you, right, all the time, or it's too heavy to carry around. So what you want to build is like have a long running time, easy to carry on. So that's we come up with this idea. It's not a whole piece, but it's part of that. That's where you can see what it's a bit ugly, but that's where you can see what we built. So I already sent a final product. So final product we built can last 3 hours in a. So they have two batteries. So similar to the Ryobi battery thing. So they have two battery here and have a roller, have a motor connecting here, have the vacuum being here, have a roller going down here, is suction. Yeah, a lot of magnetic here because we love magnet. Right now we don't have a, because when you need to change your roller for the vacuum cleaner, you need to have a screwdriver or coin to that for the Dyson one, right? But in a real scenario, they don't want to carry a pin all the time. So we need some sort of magnetic connector. So have a 2 or 3 changing for the maintenance, especially changing the wheels, changing the rollers, everything. And we also have a vacuum full detection. So you want to clean the bin, empty the bin when the bin is full. And then there's an IoT in there. So it all connect to the cloud. So it actually sense how long does it run, because normally when you send the cleaning out, she said, I already clean all of 5 floors. And from the record from the log, the cleaner only run, or the vacuum only run for 20 minutes. How can you so there's something for the service company to log all the events, and also for maintenance, right? Because this cleaner vacuum has been running for 30, 60 hours. That means you need to change your roller or change your motor or change your wheel. So there's something kind of for that. So what I'm building is a prototype. So then she went to a Chinese manufacturer to make it to a commercial products. So that's kind of with something. I don't know. I don't know how she goes, but she took to the second stage. So we went through Queensland Innovation Fund, that she paid 50%, and Queensland government paid 50%. So we built this prototype, and then there's a stage 2 funding as well, commercialization funding as well, right? Once you have prototype down, you can apply for another funding up to 100K or something, 200K. Yeah, exactly. Yeah, something like that. Then you can turn this one and work with a Chinese manufacturer to turn that into the reality. So that's something we are able to do. So it's not just so we can 3D printing. Now we can do a CNC, we can do the PCB manufacturing, we can do the software. So all in one. So we don't need to send out to different manufacturers to make different things, right? So our student can work this as well. So they have a skill from 3D printing, 3D modeling, PCB, software, image processing, Amazon Cloud, AWS, dashboard, all the things. So from the first, that's why we want to teach our students. You can have a whole system engineer, right? You are not just doing a traditional mechanical engineer, civil engineer, chemical engineer, but now to me, IoT is more like a system engineer. You're trying to learn a bit of everything, and then it's perfect for a startup. You go like Kim and other people, right? They graduate. Yeah, Kim's here, right? So after graduate, yes. Yeah, sort of like that. So there are two different directions to me for engineer. One is going to company, for example, like SpaceX. You want to innovate, right? You want to send people to Mars to have all this high tech. You need a lot of so it's kind of an innovative part. So we teach that how to innovate, how to design something that's creative, that's solving problems. Another part is you just go traditional job, like go to a sugar mill, be automation. So less innovative, but just follow protocols. So we have this to train students with following protocols, have the skill. We have some other projects in the second and third year, allow them to create their own project. We can see some of their past project over there to build something creative. I think we can move over there.
Yes.
Yep. So all the things here, majority of them are just 3D printed toys or demos. That's for attracting young kids coming to engineers. So there we can say that for most of the kids coming here, for all the two are coming here, I always say to them that the ultimate form of engineering is the Iron Man suit, right? The Iron Man suit have every component of a technology, every component engineering. You have a rocket, like a the I don't know, like a aerodynamic, have a AI, has a mechanical part, has the software part, has the ion reactor, all the things for the. So if you want to be an Iron Man, like building Iron Man suit, it's not that yet, but it can go to that way. So for today's technology, you can almost build a full suit, like a without the AI function, without the flying function. So for the majority part, you can build most of that. For the you can have the Java's personal assistant over there to do lots of things. You have image processing. You might see lots of YouTubers, they have built similar like that. So what we built here is just some people engagement mostly. When they come to open day, when you come to lab, you can see, oh, I can have an Iron Man suit. I can turn that in. Just not sure. It's been for 3 years. That's been falling on the floor multiple times. Have the super glue all together. But this just make kids more interesting. Oh, this is what you can build. You can actually build this right now, not just toys, right? It's coming to life by today's technology, similar to this one. Yeah, you can try. You can actually lift it up. You have a small hand, you can put it in already. So just
Yeah, there you go.
all right. So something like that. So this is just more lots of these things are just for entertainment. So like there's for selling the engine, it's also a demo because for the majority of even our student, they very little of them understand how a combustion engine work, right? A lot of them can't understand what's inside, what's this. And then this is just a cool demonstration. You can take this in apart. Come over if you want to have a close look. It doesn't. You can take this into apart, just see how combustion engine work. It's just turn I don't know, just some I don't know physics into reality, some the real thing into reality. So you can see that in action, and all of that is just built by 3D printing. So you can imagine how wow in the past, like 5 years ago, 10 years ago, you can't even build this thing like in. But now you can 3D print everything, even though it's in plastic. But we are getting better and better with different materials to do that. This thing it's a jet engine that's also a model that's using in the commercial airplane line. So hopefully, be rusty, but I generate a lot of fuel. And you can do a reverse thrust. You might need some maintenance anyway. So you can do a reverse thrust like the actual jet engine when they landing, they turn on a reverse thrust and stop that, right? So just fun stuff. So all the things are here fun, have lots of jet engine models, some smart thing. Another cool thing that I won't be able to demo today, sadly, it's the Rubik's Cube solver. So that's our third year student projects. So basically, if, you can come closer if you want to have a look. That tell you what a third year student can do. So you can see a lot of different components here, right? Not just software. Hello. Yes. So in the third year, in the second year, they do a dedicated project, but in the third year, they can create any project you want. King, what project did you do in the 3501? No, 3501. Embedded system, Bronson, the one Bronson taught. yeah, anyway, so they can choose whatever project they want to work on. They can I forgot that anyway. But you build a design project for the engine monitoring thing, right? In the 4th year project as well. So they have 2 design projects. In the 3rd year, they are more focused on the technical aspects. So they're building something cool, innovative, can solve something, for example, this one. But in the 4th year, we have another project called design projects. So what this focus is not just cool, not just fun, but actually something you can turn into a product that have a market potential, not just building a toy. But then what they need to investigate is the market potential, is the price, competitors, all these things. So they have to consider more of this part. So some of the students, they turn their 3rd year project, prototyping, a technical part, and then in the 4th year they do some marketing research, other things, and turn that into a real products. So that's they need to propose a funding proposal to how do you make this thing. So definitely not this one, but something close to the marketing perspective. So for this one, you can see there are a few different components. The first one is the casing, the cage, whatever. It's basically what they can do in 3D printing. So for solving a cube, you first need to design a case that housing all these 6 different motors. So you have 6 faces, they have 6 motors. Each motor is controlling one of the face. And then the second thing they need to do is they need to control motors, right? So you need to make sure that, because when you're solving the cube, either 90-degree, 180-degree, 270-degree, you want to make sure your motor turns exactly 90-degree, not 70-degree like that. If you turn something like that, the second move won't be able to achieve. So that means they have to do some control mechanism. That's what they do in the 3rd year. They learn some PID control. So they build a circuit board, something like that, can read the rotation angle of the shaft, and then to adjust that using the PID controller to make sure that they're actually in 90-degree perfectly. So that's the second step, building a circuit board, building software to control that. And the last step is the algorithm. How do you solve a cube? There's so many different patterns, so many different algorithms. So what I did is here you have 2 cameras, webcams on the top and bottom. So each of them will capture 3 faces of this cube. So then you use machine learning. So they can choose they can choose whatever algorithm they want to choose, either conventional image processing or AI image recognition. Basically, they need to recognize the color of each of the a part or a grid of this face, right? And once they recognize that, they can match. So there are tons of algorithms for solving Rubik's cube. Basically, you just map the color to the front, back, top, bottom, left, and right, and you can solve the cube. And then they talk to the machine. So they solve the cube on the computer and then tell so this one turn 90-degree first, this one turn 90-degree later, this one turn 203-degree. So then you solve the cube automatically. So that's the kind of principle. So it goes from 1st year 3D modeling, 2nd year motor control, 3rd year image processing and AI. So from 1st year to 3rd year, they can build this thing after 3rd year. So that's basically it's a perfect example to showcase what a student can do after 3 years studying engineering here. And also what you can do to build something like this. So it has all the components from 3D printing, from a little bit CNC, from PCB milling, from image processing. So from hardware to software to machine learning, all these parts. So that's what I can do. Well, let's move to, yeah, we'll show that later anyway. So yeah, I can operate that right later. So we have lots of we have lots of 3D printing machine. That's we do most of the majority of the job by 3D printing because it's cheap, it's faster. For prototyping, you don't need an actual CNC machine. For the non-critical parts, you can non-mechanical part, you can 3D printing very quickly. We have a few different printers here. They can print material like a normal PLA, just very basic material, to the fiber, like a PLA fiber or fiber infused ABS or nylon, all these materials. So can make a strong parts. I don't have any nylon parts here anyway. So they can make a few parts. And also we have like a resin printer on the back that's print for different things. For example, this is broken leg, Spider-Man is print that one. And the cool chess set, it's printing using a resin print as well. So it's not for like a mechanical part, it's more for model. You're building some model, building a skeleton or brain model or a heart model, like using this run very good. Sure.
Is like the future of additive manufacturing and the future of 3D printing. You've obviously seen this with housing. We've seen houses, especially if everyone's following in Japan, what's happening, 3D printing of housing. We're in a housing crisis right now. So how can additive manufacturing be impactful for housing, but 3D printing? We also had some discussions with an interesting group of students that came through and also industry in relation to, could this not be food?
Yeah,
We're
they're
seeing
printing chocolate. Like
3D
right now, they have
printing
chocolate machine,
chocolate,
pancakes.
cakes.
Yeah.
Yeah. But if you think about the future of medication, could this not be pharmaceuticals?
Yeah, they have
Okay.
little tiny human heart by 3D
Yeah.
printed. Not full heart, but the tiny
So,
one.
so the organs.
Yeah, organs. Yeah,
medication.
that's the future of 3D printing, not just toys, but actually operational parts or
Yes, yes, they're really good, and that's a great if you're looking for a good field project or a field visit, it's really good, and they're very open to having
Yes.
groups go in and have a look at the robotics in the farm.
Yeah, we had a student like 2 years ago working on with the Allies Pharmacy, try to identify empty shelves and picking up the pieces. Right, so that's a student project for that. So I have few collaborations with different things. Yeah.
So if you think of these spools, so these are the spools that fit in 3D printing, right? And that basically does the 3D printing. But you know, what's stopping us not thinking about this could actually be some form of medication,
Yeah.
you know, and that's what we're having a discussion with the pharmacies. You're working in the field of smoothies and food, right? So, you know, I think there's lots of applications and ways that we can start thinking about that in additive manufacturing.
Sure.
Any other cool projects anyone's working on for 3D printing or additive manufacturing? Yep. What are you working on, Vicky?
With the Australian Impact Group. With the Australian Impact Group, so I just want a model, like a model of the cyber hero that's in the background, like in the gamification that I'm building. So yeah, I had a design there. Probably have a yarn with you later
That's
for that one to just print it out every 3D right, and then ready for the I think we launching in Brisbane sometimes in August, September.
Yep.
Yeah. So I have one project to 3D print here.
Yeah.
So what happened is that one of the problems in 3D printing nowadays is the waste, because there are a lot of waste in plastics. So I'm not sure right now, but we try to create a biopolymers to replace that.
Yes.
So there are any projects in that?
So there are two projects I would in mind. One is just a spreader to straight to cover to stretch the 3D printing like a waste printing to a smaller pallet, and then they will feed back to the melt bag and then pull a string again, so you can reuse the spool. The spool here. So for example, this spool, not from us, but from Prusa, it's coming from waste product. So the waste 3D printing. Another way I was building earlier is the PET kind of the normal like normal plastic bottle, a PET bottle, like a filament puller. So basically you have the bottle, you cut them into small stripes, and then you go into a extruder, and then you pull out, become a string. So you can use that for print as well. So that's a good project for environmental. You can turn all these bottles back to a 3D print. You can print parts with that. So there are a few different methods to work around that, and then a lot of manufacturing they have just making biodegradable PLA. So it's kind of direction of that. We don't want to make lots of waste products, right? Yeah.
Actually, and have a look at the more bots. We've got Spot.
Not yet.
Not yet.
So
The metal.
so this is a
Metal printer.
CNC machine on 3-axis we just recently got. So you can make metal parts rather than a plastic part. If you need some actual machinery make, we haven't figured out how to make good parts yet. But for example, we can carve this. This not have a good accuracy. Then what else we have in the part? Yeah, it goes 10 millimeter thick. And then where's the other metal part we make? So this vacuum coming here, and then we have to clean that up. Oh, that's a Batman. The Batman tag I made just for fun. Yeah. Anyway, so you can actually make some aluminum part, even steel parts for that. Not big parts. Not well. We're trying to get a force access to this or to get it better, so you can manufacture some metal parts. And we also have a laser cutter here that you can cut lots of different things for small kind of plates. You can cut acrylic, cut timber, everything, MDF. So it's handy for cutting that. So I have different type of manufacturing. You can make different things. And this table first. So there are 2 projects or 3 projects on this table. It's been messy, but that's how I generate works with everything everywhere because I have 3 projects in one table. So I have to, I just everywhere anyway. So one project for this one, 1, 2, 3, that's with Mariba Air Museum. Have anyone been there? Aviation Museum. So that's with so what they recently got funding for is building kind of entertainment pilot training platforms. You see the commercial actual one. You have a big cockpit in have a 3-axis, have a motor down in that. So when the pilot is training that, they operate the plane inside and the whole cockpit and then move around with the plane. But they won't be able to build that. But what they build is more for entertainment for kids. When they come to museum, they can actually, it's similar to the ride you find in the theme park, right? Like for 4-degree, like a 4D ride. That normally what they say. Yeah, exactly like that. But it's not like that. But we want to build a chip like a actually just for kids. So what they build is here we have this one logic controller connect to the Microsoft Flight Simulator or X-Plane. They have different flight simulator, but it doesn't matter. So you can. So what we build is to have a Raspberry Pi here to receive the data because wirelessly receive the data using some API UDP service from the Microsoft Flight Simulator and or explain back to the Raspberry Pi. So Raspberry will process the information. What's the roll? What's the pitch? What's the yaw of the airplane? What's the throttle level? And then this one will connect to this controller, this step motor controller. And then this one will connect to the step motor. And basically will tell the motor how many degree, how many steps you need to run to 10s. So, and there's an auto motor down there to control the yaw. So these 2 are control the roll and pitch for them. So 2 degree of freedom. And just it's not a very difficult project, but it's more of a link to the actual industry for the STEM program. And the other one here is more interesting. It's to one of our recent project working with staff, Queensland, and a lot of different whole innovation, if anyone have heard of that. So basically it's for fruit fly sorting machine. So we're also building smart trap as well. Basically, they will send out these traps, go into the field, collect lots of fruit flies. And what they currently doing is has a lot of actual human to handpick one flies, go into a microscope or something to detect the species, because what they want to identify is if there's any exotic flies coming into Queensland and if that danger or whatever, something like that. But that's very time consuming, especially if they have hundreds of trap coming in every week, something like that. They have 1,000 fly in there. It will take them forever to handpick and then scan those fly. And what we're trying to build is an automate process, like Sam talked about. There are lots of automation for engineering, so we're trying to solve problem with automation, like with robotic, all the things. So what this does, we have a bag of dead flies here that are used for taste. I still have 2 here. There's a fly everywhere. Well, they are dead, but should be fine. So what this does is have, I think it's working. So this is not finished, but this is just a part of that. And then you have a vibration. I just make sure they don't. So you see the fly traveling. Come on, stop. So, and then there's a sensor here to detect when this fly is coming, and it will stop. And we'll put a what we call a near infrared spectrometer here, and the fly will stop here. And then the scanner will scan that based on the wavelengths, everything. We do a machine learning algorithm, try to figure out what species this fly is, and then it will stop at display. And then based on that, you have a different sorter to different places. So this is an automation process. Once you have 1,000 fly going there, you will go to the carousel. You will going up, pick them up. So this is a prototyping, but we're trying to make it have a owner student trying to make it more robust, adaptive, because the current issue is that the flies, when they come in, they always tangle together. That's a very challenging task to separate them. And then how do we separate? And sometimes it's coming wet because they have a rain, everything. So they are not, so these are clean flies in the lab. So they're perfectly, they are dry, they are dead, they are not wet. So it can be separated here, but there's another step prior to this. You need to how to dry them, how to separate them, untangle the legs, everything. And there are lots of things here. How do you make sure they align perfectly? You don't want two fly go into a play scanning surface at once, right? You want them one at a time. So there's something you need to work out here. So what I was doing is working on is using image processing. There are a few different methods. You can use a sensor to detect that. But what he's trying to propose is use a camera. So you have maybe have 10 flies here. They're all randomly distributed. Use image processing to detect what's the distance between them, what's the XY position between them. Then after that, you can design a smart mechanism trying to, after this thing, make sure, like a Amazon warehouse, they have a tons of packages coming in. Eventually, it will go into like nicely one at a time. So, but this is for flies. The challenges for flies, they are so tiny. They're just, 3 millimeters in width and then just half gram or less than half gram of that. So it's very challenging for the traditional sensor like an optical laser or break-beam sensor. You can't even break them. So because they are so small. And then this big part, that's the wing, that's the transparent part. It doesn't really block light or anything. So there's a student working on that. And also there's a student working on how can we detect the fly in a trap already before they go into lab? That will save lots of trouble, right? So then if you put some smart sensors inside the trap, when the fly comes in, it goes through this scanner detection. It might not be able to identify exactly species, but it should be able to detect whether it's a big one, small one, the size, the speed.
By photograph, because each species has a specific pattern in the thorax.
But it's tiny, so that's a challenge. Yeah. So the challenge in the trap is that because it's distributed in the field, you don't have battery, you don't have a lot of things. You want to make it like light. You don't want the whole thing have a big chunk of a machine under the trap, right? You want to make it light. So we are not necessarily want to identify the specific species of fly. We just have some preliminary analysis whether this fly is a bit bigger, this one is small. So you can have some initial result before going to here. You can already separate half of them or 20% of them before they so save your workload. So it's something like that.
So that is for the field or
Oh, for the lab. This is for the lab. So there's another one for the
for the
field.
because the fruit flies, the problem that we have, especially in Queensland about the fruit flies.
Yes.
It should be amazing. There are a trap that is the McFly trap.
Yep.
And we use that one to collect the flies.
Yes.
So
So
you can develop something like that. It's really smart because what I mean, I'm biology, so what I had to do in my thesis in Colombia was to identify, I remember that I had to identify probably around 2,000 individuals
Yeah.
by eyes.
Yeah, yeah,
And
it's challenging. So something like that. So not just for fly, it can for all different insects, right? So anything, ants, you can put in here and then scan that. So the only thing you need to modify is the software. After that, you need to adapt to different. Yes. So this was traditional used for grain, for rice, for those kind of separate. That's easy because they are like a solid, just easy to scan, easy to separate. So fly is a bit challenging. That's why we need to some customization for that for flies. So that's another project. Now going to the what Sam wants the most. Let me see. I can get it.
Yeah.
So this is yeah, I have to control using my phone. So there are so there are 6 legs. Each leg have a 3 servos. Each leg has a 3 degree of freedom control. And then what it does, no, it won't jump. So I just need to connect to the same Wi-Fi so I can find out where it is. So it's control. There's a servo controller under to control the 12 servos, and the form here is just communicate with the servo controller for the different, because the originally I want to use the Raspberry Pi or other thing, but the form itself it's perfect for everything, right? Because yeah, it's a accelerometer, have everything in there to native support, so you can develop a app easy to read those values. One thing, what's the right to adjust the hopefully it works.
Can I take this home to battle with my cats?
Oh, it might not be.
Oh my god, that'd be the perfect thing for cats.
It might be too weak.
Let's see something like that for us and see them run. It'll be fun. There we go.
So what this does just
Oh my god.
not this one.
Yeah, this is what's coming in at apocalypse.
Yes.
It's a lot.
Let's see.
Inspection was designed for exploration. Flexibility.
That is really cool.
And go. Yes, it's scare. It's race.
Oh, this is the perfect video. So, yeah.
Thank you. Oh, it's 1 hour already. You can go off-road as well, so you can live be higher. Yeah.
Just for the people online, we're pretty much finishing up this session. You can stay tuned just to watch the spider walking around and doing stuff. But thank you for joining us. And yeah, and we'll see you till next time. We'll see you next time.